Welcome back, statistics students. This is Mr. Marquetta, and I'm here to help you guys today with chapter 20 of our textbook, which is comparing to proportions. Tonight's lesson is being recorded, and students are in the Zoom with us. They may come and talk with us, or they may also send messages, and if they do, I'll be answering those questions. So if you have anything you'd like to talk about, please don't be afraid to unmute. Also, those of you who are watching on YouTube, please take advantage of the fact that you can pause and fast forward and such to look at different formulas and things that we're going to do tonight. So tonight we're talking about chapter 20, comparing to proportions. Starting with our objectives, we're going to discuss tonight two sample problems with proportions, which is kind of similar to before when we had two sample problems with means, except now it's going to be about proportions and not means of a group of data. Also, we're going to discuss the sampling distribution of the difference between the two proportions. And you probably will recall that when we did two sample problems with means, there was a subtraction there. There was a difference that we used. And it's very much the same idea with our proportions. Also, we're going to talk about large sample confidence intervals for comparing, and then we're going to talk about more accurate confidence intervals for comparing. Very similar to what we did last time. The +4 rule does apply, and we're going to show how you can use that for two samples instead of one. Also, we're going to show you how to write hypothesis test out, including hypotheses, and then the math behind it, and then using tables and coming up with a conclusion statement. Last but not least, we're going to do an application in the health sciences today about relative risk and odds ratios and a couple of important measurements that have to do with a person's improvement between a placebo and a treatment. So first, let's start by talking about two independent samples. Usually you need to compare two treatments with two independent samples. So for large enough samples, we assume it's normal. And as you can see here, for the first time, we have subscripts on our P's. Before, we didn't have that because we had one proportion only. Now you're doing two different samples, so you have two different proportions. And those two samples they don't have to be equal either. They don't have to be the same amount of participants in the samples. So if you look closely here, I'd like to kind of highlight that. Here you see the sampling distribution of P hat 1 minus P hat 2. I just kind of want to accentuate this for a minute and look closely at this with me, okay? You'll see here that we have some P1s, and they're associated with N1, okay? So that's the first group. And N doesn't have to be the same for the two groups. It could be different. For example, maybe in group 1, you have N equals 120. And in group 2, you have N equals 126. Might be just like that. So it's important to note that those N's are there in that way. And then also for the second group, we have these measurements here. So you can see that the standard deviation does take into account the proportion for both of the groups and also the sample size of both groups. And that is those variables come into play when you're trying to find the standard deviation. Remember, we don't know P1 or P2, and recall P itself is the proportion of the entire population. What we are finding is P hat, and when we do estimates, we like to use P tilde, but P itself is the proportion of the whole population. So here, what we're trying to say is that in this situation, remember, we don't know what the proportion of the entire population is. So it's going to have to be something of an estimate. So first, let's talk about how to make a confidence interval for two proportions. And again, you'll see the standard deviation does appear just like we had it before. Here it is again. And of course, it's being used to determine our standard error. And the standard error is part of what you need for the margin. So in a confidence interval, first you have the mean or the proportion. In the case of a two sample, you have the difference of the means, or in this lesson today, the difference of the proportions. So there's a difference of the proportions. And remember, it's plus or minus M, and M is the margin of error. So the first step in trying to figure out what the confidence interval would be is finding those P hats, the proportions, and subtracting them to get the difference, which is in the first red box. Then after that, you start focusing on trying to find out what the margin is. The first step of trying to find the margin has to do with figuring out Z star. Z star is something you find in your table. If you remember, it's dependent on whatever specific confidence you're using. So if you're using a 95% confidence or a 99% confidence, whatever confidence you're using, you use the table and it will tell you what Z star is supposed to be. Then after you go and find that number on the table and use it for Z star, then you start thinking about the standard error of the mean, which is right here. And it's all of this stuff that we have right here. And you put all that information in and do a little calculation. And when you're done, you have the confidence interval. You have a number, which is the difference of the two proportions, and then added to it the margin, and then also the margin subtracted from it, which gives you an orbit. Remember, we talked about the orbit and about how the range of numbers for an interval going from here to here, and your final statement will be something along the lines of, with 95% confidence, or whatever the confidence interval is, I can predict that the population proportion difference is somewhere between this number and that number. And that's the concept of a confidence interval. Okay, friends, so let's see if we can put that into motion and use an example or two to illustrate that. How much does the cholesterol lowering drug G, and I'm not going to try to pronounce that, we're going to call it drug G, okay? How much does this drug G help reduce the risk of a heart attack? We compare the incidence of heart attack over a 5-year period for 2 random samples of middle-aged men taking either the drug or the placebo. So we have a lot of things going on here. First of all, we have this drug G that we're going to figure out. We're trying to figure out if it's effective. So we get 2 different samples of a specific criteria. In this case, the criteria is middle-aged men that are, well, it's just middle-aged men that are going to be taking have a cholesterol issue. Then you say one of these groups is the placebo group or the control group, and one of these is the treatment group, or the group that gets the drug G. And then after you do that, you look at each group separately, and you look in the first group, the placebo group, and say, what's the proportion here of people that had an improvement in their health? And you do the same thing looking at the treatment group. And now you have a p-hat-1 and a p-hat-2. Also note, you're going to have an n1 and an n2, which is the number of people in each of those 2 groups. That information gets all put together here to figure out the confidence interval based on a specific percentage. So let's take a look at how we would construct the confidence interval in a situation like this. First, we would go and figure out what p-hat-1 is and what p-hat-2 is. Now, in the PowerPoint slide, they didn't explain how or why, but they basically just made numbers up and said, so let's say, for example, you did that whole thing that I just explained. You get the 2 groups, one is a control, one is a treatment. You find out the proportion of people in the one, it's p-hat-1. You find the proportion, etc. Let's pretend that these are the actual numbers that came out of that study right here. So for p-hat-1, which is here and here, apparently that was the number 0.0273. And then 1 minus that number is what you see here. And for that first group, there were 2,051 middle-aged men. Now for the second group, we'll highlight that with red. We have p-hat-2, which is this figure, and then 1 minus that, which is this figure, and then over the amount of middle-aged men in group 2, which is this figure. And then don't forget the whole thing has a big square root over it, and do all of your math, and you get 0.0057. Great. All right, so 0.0057, that is the standard error of the mean. I can use that to come up with a confidence interval. First, what I would do is subtract the 2 proportions. As you see, here they are, right here and here. I'd subtract the 2 of those to get this part right here. And then I would go find Z star based on whatever the confidence interval was, or the confidence level was that they told me. And then I would use that times the standard error of the mean, which is this funny number right here. And then I'd have my confidence interval. So in this situation, you'll see that the table has all those numbers I just highlighted in the boxes for you. They should have shown you the table before they showed you the formula. It might have been a little bit more clear. But anyway, in this situation, you'll notice we have the ends are noted here. And here are the proportions, but in percentage form that we just looked at. And we're asking you this time for a 90% confidence interval. Okay, so 90% confidence interval, when you go to 90% and you look up 90% Z star, you actually get this number in the table right here. So we'll take that number and use that as Z star. Also, we're going to use the difference of the two proportions, which is right here. And we're going to use the standard error of the mean, which we found, which was that large square root. And we're going to wind up with this final solution that looks like this. Now, this is the confidence interval with a plus or minus. If you want it as an actual interval from what to what, you do 0.014 minus 0.009. And that is 0.05. Right. And then you do 0.14 plus 0.009, and that's going to be 2.3. Now notice those are percentage points. So it's 0.5 percentage points is the same as 0.005. And they weren't really very clear on that, but I just want to mention that because one of the things that keeps on coming up here, just want to write that in there so that we can talk about for just a minute. They like to play games with percents versus decimals. And it is important when you're looking at these things to see the way that they word things in the word problem. Just make sure that you know if they're asking for percentage points, then it means change it back to a percentage, please. So it was 0.005, but as a percent, that's 0.5%. So percentage points means percent. It's like writing the percent sign. And just so that you know when you see that, this is the way it is because it's the idea of 0.014 plus minus 0.009 equals 0.05, which is 0.5 percentage points. I'm calling them PP for percentage points. And to get the other one, of course, you would add. I'll put that one up here. Maybe we'll make that one purple. So that would be 0.014 plus 0.009, which is going to be equal to 0.023, which is 23 pp. Okay, so this is how we come up with a confidence interval. First, in the case of two samples, you subtract the two proportions, and then you do plus or minus. Then you got to go find Z star, which is not hard to do. It's based on what your confidence interval is. You go to table C and find out what that number is. Then find the standard error of the mean, which is that big square root, and it involves p hat 1 and n1 and p hat 2 and n2. Figure all that out. And then after you're done with that, you can take that figure times Z star and add it to the difference and subtract it from the difference. And then you have your confidence interval. Now that is a very accurate and wonderful confidence interval, but of course we can do better. We can use the +4 method, and that's the next idea that we're going to talk about. If you are in a situation where you have a small sample size and you're concerned that your sample size is not quite large enough to really be appropriate for assuming that it's normal such that you're able to conduct a test with a two sample, then you might want to go and use the +4 method, which is something of a correction to try to make your P a little bit more appropriate. We like to call that P tilde. And the reason why it's P tilde is because it's not P hat, meaning an estimate from your data. It's the estimate of your data, but enhanced slightly. So we're calling it P tilde. Now, P tilde has been enhanced before when we had one sample, where in that situation, on the top, I would add 2 right here. Let me change that color. On the top, I would add 2 to this, and then I would add 4 to the bottom. Now, that was the way we did it before because that was one sample proportion tests. Now we have 2 sample proportion tests. So to have the 2 and the 4, we have 1 and 1 on the top makes the 2 on the top, and 2 and 2 on the bottom makes the 4 on the bottom. So in other words, when you do the +4 correction to your P hat to make it into P tilde, you don't have 1 P hat, you have 2 P hats. You have P hat 1 and P hat 2. So now you have P tilde 1 and P tilde 2, but they have to share the 2 out of 4. Each of them gets 1 on the top and each of them gets 2 on the bottom. So it's not hard to do. It's just a matter of remembering that adorable little technique that you want to go in there and just put those numbers in there so that that works. And then what you're looking at here is the same thing, except all of the hats have been replaced with tildes, meaning do it again. using the p figure that we find for p tilde 1 and p tilde 2, and just put them all in the same positions. Don't forget when you do this, though, that the new sample size is n1 plus 2 and n2 plus 2. And that's like that because of this and this. That's the reason why. So just remember that that's the only difference now that you're looking at, that you see in the difference between the p hat confidence interval and the p tilde confidence interval, is these denominators have the plus 2 in them as well. And don't forget that you're figuring out p tilde 1 and p tilde 2 using that little extra plus 4 method with the 1 on top and the 2 on bottom. Okay, so that's what you would do if you were trying to figure out something when you had a very small size. Look, it says the plus 4 method, again, produces more accurate confidence intervals. We act as if we had 4 additional observations and 1 success and 1 failure in each of the 2. That's why it's like there's 2 total and only 1 of them came out the way we wanted it. Okay, here's an example that employs the plus 4 concept. Researchers compared oral health in 46 young adult males wearing a tongue piercing and a control group of 46 young adult males without a tongue piercing. They found that 38 individuals with the TP group and 26 in the control group had enamel cracks. We want to estimate with a 95% confidence the difference between the proportions of individuals with enamel cracks among young adult males with and without the tongue piercing. So 1 count is too low for the large sample. In other words, look closely up there at how in the TB group, we have a total of 46 young adult males. And in the TP group, we have a total of 38 who had enamel cracks. If 38 of them had enamel cracks, 38 out of the 46, that means that only 8 out of the 46 did not have cracks. Now remember how we had to have at least 10, or even at least 5. Sometimes they say at least 5. In this case, it's at least 10. We don't have at least 10 cases in our story. And that's going to make it less than normal and hard to make predictions and assertions using our hypotheses. So this is a great example of why you would use the plus 4 method. In this case, one of the proportions is significantly unfair. We only have 8 people that did not have enamel cracks in that group. That's too low. We have to have at least 10 failures and at least 10 successes in each proportion for it to be appropriate. If it's not, then you have to use the plus 4 example. So in this situation, we are going to apply the plus 4 example. We're going to use the 38 out of 46, and we're also going to use the 26 out of 46. And those are going to be the 2 different proportions that we're going to use. And notice in both cases, 46 is the n for both of them. So let's take a look now at the math for that. And you'll see what they did was they tried to make it really clear by not just making a p hat 1 and p hat 2, rather, excuse me, p tilde 1 and p tilde 2. They went a little further and wrote exactly what kind of the group it is so that you don't have to think too hard about which one it is. So don't let it bother you when you see words like that written there. The reason why those words are there is to make it easier for us to understand. For example, the fact that this is p hat TP and that I have measurements associated with the TP, which is tongue piercing group. You know, I don't like it that this is so thick. Let me fix that. There we go. Much better. So you have the TP here. Here, see, all this fraction has all TP measurements. Then, likewise, you have all of these fractions, which have all control measurements here, here, and it's just as if it said p tilde 1 and p tilde 2, but 1 is the TP and 2 is the control. So what they did in this part right here in this whole part is they rewrote the entire margin formula out using the new subscripts to represent the group of TP and the group of control. And since it is a p tilde formula, we're going to include a sample size of +2 on the bottom for each situation. And then you just plug in all your numbers. These are the numbers that we talked about earlier right here, 38 out of 46, and then 26 out of 46. Notice that we've done the +4 method here and here. And now we have new p-hats. Here they are, but they're p-tildes though, because we did the +4 on them. Then you could subtract them and you have the 0.25. That's what's gonna go right here, 0.25. Then you go find Z star in the table. In this case, we're talking about a 95% confidence interval. So Z star for 95% is a 1.96. So that's the number that came out of the table. And then you just carefully substitute all of these important numbers in and do all of your math here, and you get this as your margin. Now you can take the margin along with Z star, multiply them, and then that is going to be your orbit around the difference. The difference is 0.25, and then that product Z star times the margin is going to be added to that number and subtracted from that number. Now you have an interval. The numbers turn out to look just like this. You do 0.25 plus or minus 0.179, and if you do it plus, you get this number. If you do it minus, you get this number. Now, as percentage points, you can look at that and say that this is a 7 percentage point and this is 43 percentage point in that way. And if you change into a percentage point without a decimal, of course, you're going to get those as your answers for this one. 0.71 is the 7 percentage points. 0.429 is going to be the 43 percentage points. Okay. All right, very good. Now, carrying on, let's talk now about how you would do a hypothesis test for two proportions. This is the first time we're looking at a hypothesis test that has two equal signs in it. The reason why it has two equal signs in it like that is to try to demonstrate that not only are the two proportions equal, but they also equal the population as well. So the null hypothesis is that there is no difference between the two proportions, and further, there is no difference between either of the proportions and the actual population proportion, meaning that whatever your hypothesis or your hunch or your educated guess was not right on. That's what the null hypothesis says. We're hoping that we can gather evidence to support the alternative hypothesis, which says something else about the connection between the proportions. Maybe that one proportion is greater than the other, or that the population proportion is less than it should be, or less than what they say it is, or things like that. And in that regard, we're going to start constructing HA, which is the alternative hypothesis. Usually in that case, we have a greater than sign or a less than sign, and we'll see a couple of examples of that tonight too. Right. So if HO is true, then we are sampling twice from the same population, and we can pool the information from both samples to estimate P. So remember before when we were talking about two sample means, right? We were doing means to two sample tests. Now, in that case, they told you do not ever pool. Remember that? And it said pooling is strictly, is significantly or is definitely discouraged. Do not do any pooling. Here, now you're doing proportions. When it comes to proportions, since they're such simple measurements, it's either yes or no for each person, you can pool them and you can make a new group. And that's the reason why it's believed when you're doing two sample proportion tests. If you initially fail to reject the HO, then you can try it again if you use a pooled example. So how do you find pooled? Well, pooled means put them together. So if I had a group here and a group there and I pooled them, I just put them all in the same room. So look at what P hat is now. And now for the first time, looking at two sample tests, we have P hat. We always had P hat 1 or P hat 2 so far, right? Well, now we have just the good old P hat as if we're in our last lesson, and that's because we're going to look at it now like it's just a one sample proportion test, like last lesson was. So when you pool, that's ultimately really kind of what happens. Now, we're going to go ahead and pool them. So when we pool them, we get the total successes, which is the total of the two numerators on the top, and then the total observations, which is add up the total number of people in both groups. Divide and you have P hat. It's as simple as that. When it comes to finding Z though, and Z, this is a little bit special. Make sure that for Z, you remember what your P hat 1 was and what your P hat 2 was. You have to go and find those, because not just does Z employ P hat. Look, here's P hat, which you just found. It also needs P hat 1. I'll give that a double box. And P hat 2. See what I'm saying, guys? Okay, so the p hat 1 and the p hat 2 also has to go and get calculated. Remember, it's not hard to find p hat. All you have to do is take the number of successes out of the total group. It's just a fraction. So finding p hat 1 and p hat 2 is not hard. Finding p hat itself is just a function of those two. Be careful how you do it, but that's how you do it. And then don't forget, each of the two groups has a different sample size. So make sure you put them in this way. And go and do all your math and calculate it out, and you'll get a z-score. Remember what comes next in the test? You use the z-score, you look it up on the table, you go find the p-value, or you could use it in the Excel and find out what the p-value is, same way that you would find a t-value. Okay. So here's an example. This is about a specific process. It's a procedure, a surgical procedure. It's called gastric freezing. Gastric freezing was once a treatment for ulcers. Patients would swallow a deflated balloon with tubes to cool the stomach for an hour in hope of reducing acid production and relieving ulcer pain. The treatment was shown to be safe and significantly reduced ulcer pain and was widely used for years. A randomized comparative experiment later compared the outcome of gastric freezing with that of a placebo. So 28 out of the 82 patients subjected to gastric freezing improved, while 30 out of the 78 in the control group improved. So if you look at these numbers, you might be able to, in your imagination, start to formulate what those little formulas are. You could see how to find p hat 1, how to find p hat 2. If you want to find just p hat, it would be 28 plus 30 on top and 82 plus 78 on bottom, and figure out that fraction. That's just the p hat. Then you could go find z, etc. So take a close look here. Here are your hypotheses. In the case of the null hypothesis, we're saying, well, it looks like the proportion of the people that had gastric freezing, and this time we're using that lovely little subscript GF to be gastric freezing. The null hypothesis is that there is no change between those and people who didn't have it. Everybody has the same kind of improvement, whether they get it or not. That's the null hypothesis. And we're trying to find out right now if the gastric freezing is effective or not. So our hypothesis is that we think that people who got gastric freezing are going to have a greater success rate than those people who got the placebo. That's what our hypothesis is that we think that the gastric freezing is effective. So we go and test it. We gather data, and we find out these numbers, 28 out of 82 and 30 out of 78. So we can find our proportions. Not hard to do. If I do 28 out of 32, I'm sorry, 28 out of 82, excuse me. If I do that, it's going to give me this figure right here. Then if I go and figure out 30 out of 78 right here, it's going to give me this figure right here. Right? All right, next, if I need to find p hat, then I need to figure out 28 and 30, which you see right here. And then I need to figure out 82 and 78, which is right here. Now you have p hat pooled. So we have p hat pooled, you have p hat 1 and p hat 2. If it makes you feel better, you could call it p hat pooled instead of just plain p hat. Call it p hat pooled. I like that too. I'd rather have something down there. Everything else has something down there. Likewise, the ends are specific. N1, as you can see, is 82. And N2 is going to be 78, and that's very important. What is this figure right here? This is P, which is the same as this. And you put all the numbers together and you do your math and you get negative 0.57. Now, what does that mean? Negative 0.57, if you put it on the bell curve, would look like this. And if you look, in this case, the p-value is pretty big. The probability of being greater than negative 0.51 is pretty large. Look, it's more than half of the whole graph. Look at the green shading. So gastric freezing was not significantly better than this placebo because look, the p-value is not only greater than 0.1, p-value is pretty big, much greater than 0.1. So the treatment was abandoned, and now you can't get gastric freezing anymore because it's been shown that it doesn't work. So this is what we mean by using statistics to try to support the sciences and to advance with medicine. It's a big deal. that we're in a position to actually analyze something as extreme as gastric freezing. I mean, we may not necessarily be surgeons and understand anatomy to that extent, but at least we can use our science to answer questions like, is it effective or not? Just based on observations, and that's what you're looking at here. Okay, let's talk about some specific applications in healthcare. The first one we're going to talk about is RRR. It's called relative risk reduction. It is how better off you would be relative to getting a placebo versus getting a treatment. Now, I don't want you to think too deeply about this. These are pretty basic ideas. When you have two p hats, which we've had many times tonight in our examples, when you have two p hats, one of them is usually the control and one of them is usually the treatment. For example, when we had the tongue piercing, there were some people that had a tongue piercing and there were some people that did not. That was the treatment in that case. Things like that. So you can always assign one of them as control and one of them as treatment. If you want to find the relative risk reduction, all you have to do is put them into this formula, subtract them as your numerator, and then divide by the proportion of the control, and you're going to get a measurement called the relative risk reduction. So you might be asked to find the relative risk reduction when you're doing your Macmillan Achieve homework. Just make sure you come back here and look at that formula. There are two other important ones we're going to talk about that use RRR. But before we do that, let's go back to drug G and talk about that for a minute and see how we can apply that with RRR. How much does the cholesterol lowering drug G help reduce the risk of a heart attack? We compare the incidence of heart attack over a 5-year period for the two random samples of middle-aged men taking either the drug or the placebo, which we just did that. And we were familiar with that and comfortable with that. In that case, we had a total of 2,051 people that were given drug G and a total of 2,030 people who were given a placebo. If I want to find the actual proportion, I take the people that got a heart attack over the people that are in that group, gives you this percentage. And likewise for the placebo, the p-hat will be this number out of this number, which will give you this number. Now those two percentages, it's nice to talk about them as a percent per minute, but notice when you find the R and R, you have to put them in as decimals. Here they are as decimals. And once again on the bottom as a decimal. If you want to talk about RRR in terms of percentage points, you'd say it's got 34 percentage points. But the ultimate end statement of this would look something like this. The drug G reduces the risk of heart attack in middle-aged men by about 34% with all the extra stuff that they want you to say over a 5-year period of continuous treatment compared to middle-aged men taking the placebo. And then in parentheses, you'll give the measurement. What is the RRR? This time it's 34%. So the risk of a heart attack over that period is 34% smaller in the drug G group than in the placebo group. Two more little measurements that we're going to talk about, and then we'll conclude our lesson tonight. And once again, thanks so much, friends, for paying close attention to my lesson. Tonight, the last thing we're going to talk about for this lesson and for the whole course is going to be two other measurements associated with the health sciences. The first one is called the absolute risk reduction. When we were looking at this case, and you noticed that we had these two percentages of people in the group that improved. If we subtract them, we could say one group had that much more percent improvement than the other group. That subtraction is the next thing we're talking about. All you have to do to find out the absolute risk reduction is simply subtract those p-hats. That's all you have to do. And when you subtract them, it's the difference between the outcome rates, and absolute risk reduction is just that. You can use absolute risk reduction because the reciprocal of that can tell you how many patients you would need to treat. You would need to be treated to prevent one additional negative outcome. In other words, if I can find the absolute risk reduction and find the reciprocal of it, that'll tell me how many more people need to have that treatment so that I can believe that there will be one less heart attack amongst that group. It's hard to believe that that's what it is, but that is what it is. And these measurements are used on a regular basis, not just for heart attacks, but for many diseases and disorders in medicine. So the NNT, which is the number needed to treat, that is the number of patients that you would want to treat to prevent one more heart attack or one more case of the issue, one more enamel crack for the males with the tongue piercing and things like that. So look at the formula for NNT. It's just the reciprocal of ARR. So when you know the absolute reduction, the absolute risk reduction, you also know the number needed to treat. The absolute risk reduction as a reciprocal is the number needed to treat. So they are better indicators of treatment efficacy than the RRR, but the RRR is the first one you should know about, and then you could go and calculate these as well when they ask you to. So let's look at a case of that. Back to the story with the drug G. The group taking the drug G had a rate of heart attack of 1.4 percentage points lower than that of the placebo group. In other words, if you look right here, you'll see the subtraction of these two numbers, this simple subtraction. That right there is the ARR. And you could say there's a 1.4 percentage points or percentage of lower in the drug group than there was in the placebo group. Now, if we flip 0.014 like this, you're going to get this, 70.9. What is 70.9? That is the number needed to treat in order to believe that you will stop one more heart attack from happening with your drug. So on average, we need to treat about 71 men for 5 years with drug G to avoid one heart attack. All right, so that's basically everything I have for you guys tonight. I just want to say thank you so much to all of you for working so hard on Macmillan Achieve and dealing with Excel and dealing with me and also dealing with all of these extreme lessons. We've learned so much in this class. We've done sampling methods and histograms and all kinds of different measurements, the standard deviation. We used Excel a real lot. We did hypothesis tests. We talked about confidence intervals. We did a lot with inference. We really did a lot in this class, and I'm really impressed with your work. When I look at your grades in Achieve Macmillan and I see so many people that have 95s and 99s all across the board, and all of them, it's just so, I'm so impressed with you. You've done such a wonderful job as a student. And thank you, by the way, for making me look good. It feels good to write A's and A pluses and A minuses and B's and B pluses on my reports when I give grades out. So I just want to say thank you most sincerely for everything you've done in this class and all the hard work you've done. And it's been a pleasure getting to know all of you and helping you guys study. Just so that we know where we're going in the future, next week on Monday, we will have an exam 3 review. It'll be a Zoom. Again, it's optional. You do not have to come to it unless you want to. We're not exactly having a review as much as we're just going to have a conversation, if you need it, about any of the topics. And that includes any of your homework from Macmillan or any of the things that have to do with your final project. Then please be advised that on Wednesday, 12/8, you will have your third exam, and your third exam will be on Unit 3 out of eCampus, everything about inference. And it will be a 30-question multiple choice exam that has 2 points per question. And there will also be a section in Macmillan Achieve that will be titled Exam Number 3 Tech. And you'll have three days to complete that. And I'll put that up that week so you know when that's due. And that will open on that day, on that day, 12/8. That'll open for you guys, and you'll have 3 days to do that. And then the following Monday, I will be available if you need for grading conferences. That's if you feel like you want to have a conversation with me about your grade. It'll be anytime between 4:30 and 5:50. Send me an email asking me, and I'll take a block out for you out of that time, and we could talk one-on-one. Monday, 12/13 is not class. It's only meetings and conferences one-on-one between one student and myself through Zoom. So if you'd like to make a conference and talk about your grade, I'm happy to do that with you on 12/13. And then on Monday, December the 20th, your final project will be due. So please, everybody, make sure that you get the final project in on time. And that's really all I have for you guys. I'm going to stop our recording, and then we will go ahead and open the floor to any questions you might have. Thanks again for your attention. I hope you guys have a good night.